Hello everyone, welcome to Multiple Statistics and Machine Learning. In this video I will be discussing the foundations or elementary facts about matrices. As you are probably all aware is that matrices play a fundamental role in multiple statistics because of course we're looking at vector random variables, and so we naturally have to deal with random vectors and random matrices. And to do this, we need to know how to express ourselves in matrices and what you can do with matrices. And also we will frequently encounter matrix decompositions such as eigenvalue decomposition. So this is important stuff that needs to be reviewed before we can get started with the actual course. So much of this that I will discuss today you know already, probably or hopefully, from earlier courses such as linear algebra. So in the script you find in the appendix a brief refresher on matrices. So this is the recommended reading to accompany this video. So let's get started. Before I start with the matrix stuff, I'd like to show you how my handwriting looks like, especially numbers. So numbers. So my numbers look like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0. So pay attention to how my 7 looks like and how my 1 looks like. So sometimes I write the 1 also without this thing, the little thing here. So sometimes I write it like this. This is a 1 as well. And the 7 is always with the horizontal stroke here. So this is my number. So just to avoid any confusion. So that's the European spelling, basically, not the American spelling. Okay, so next we need to figure out how we distinguish matrices and vectors from scalars. So typically if you have a scalar, I would just write x, and that's just a number basically, and that's lowercase and in plain type. If you look at the printed material, it will be lowercase or plain. Sometimes it's uppercase, sometimes, but most of the time it's lowercase. Then we also need to have a way to describe vectors. So x. So in handwriting I just draw a little arrow, and that's also lowercase. But in printed, in the script, you'll find that it's printed bold. And if you find a vector that's not printed bold, then please let me know, then I can fix it in the script. So that's the convention. Lowercase bold is a vector, and a matrix is uppercase, and it has this bar in handwriting. So and printed is uppercase and bold. So this is how I should write it, but sometimes I don't put the bar or the arrow because it's clear from the context. So if it's clear from the context, then I'll do it, because otherwise it will be a bit messy. For instance, if I say A is a matrix and B is a matrix, then it's clear. So sometimes just uppercase is also fine in handwriting, but when it's printed, we always adhere to this standard. So, but when I write it here, sometimes I get a little bit sloppy. One last remark: if you please go back here. since we indicate lower and uppercase, or we reserve it for distinguishing vectors from matrices, we can't really use it to distinguish random variables from their realizations. So whether a matrix is random or a vector is random, that needs to be considered from the context. But that's, as I said, so this is a standard notation, and we follow this notation here as well. So some special matrices. So one special matrix that comes up all the time is the identity matrix. Identity matrix. That's quite an important matrix, so sometimes it also gets this subscript d. D is dimension. And it's a matrix that has ones on the diagonal and zeros on the off diagonal. And it's important because, for instance, if you have a square matrix and you take the inverse of a square matrix, then you multiply it with the matrix. So I indicate it's a matrix, but often if it's uppercase, I won't do this. I'll just do it now, and I don't do it here because it has this bar here. So this gives the identity. So if A is invertible, so not every matrix is invertible, but the inverse times the matrix gives the identity matrix. So that's why the identity matrix is important. And there's another matrix, or actually it's a vector usually, is the one vector, and that's just a column vector with all the ones in here, and that's useful for a few things, including centering matrices and a few other things. So it's good for writing things in a compact notation, but don't confuse the one with the identity matrix. So matrix operations. So I already indicated you can do the inverse. So with matrices you can do a lot of things that you can do also with normal numbers. So you can have matrix addition, A plus B, and you can also have matrix product. And here, of course, we need to make sure that these matrices, they are compatible. So in the case of addition, you want that they have the same rows and the same number of columns. And here, so basically, if you want to indicate how many rows and columns, sometimes you do this. You write, let's say, 2 times 3, then you know it has 2 rows and 3 columns. So the convention is that you first indicate the number of rows and then the number of columns. And compatibility means so for addition, so this gives C, and let's say this is D, and this is not the same as B times A if it's possible. So if it's A and B is a square matrix, then it's technically possible, but it's generally not the same thing because it's not commutative. Difficult word. Okay, so you can't interchange the order of multiplication in matrices. So I'm not going to tell how to multiply this. So it's a standard thing you can look up somewhere else, but what's more important is a special type of matrix that's called an orthogonal matrix. So an orthogonal matrix has the property that the transpose, so T is the transpose, is the inverse. So that's the same. And that has the following consequences. Namely, you can say that Q transpose Q is the same as Q transpose, and that's the identity matrix. So that's the definition of an orthogonal matrix, and they have a meaning Namely, there are rotation matrices. So if you apply them on a vector, then that has the effect of rotating the vector or reflecting the vector. So depending on the sign, it's basically technically a rotation reflection matrix. And we will encounter this later: rotation, reflection. So that's basically an operator if you apply it to a vector. And one important application of this is actually the eigenvalue decomposition of a matrix. So eigenvalue decomposition. So in our case, so matrix theory is of course something that's quite general and complex. In our case, we only usually look at real valued matrices, and often we only are interested in squared matrices, and even more special, we're interested in eigenvalue composition of symmetric square matrices. So this is just so we only look at very special cases. So let's first define what an eigenvalue is. So we have a matrix A, and then we have an eigenvector u, I. And so if we multiply these two things together and we get ui times lambda I, then, so if we have this satisfied, then the lambda I is the eigenvalue, and this is the eigenvector. So I won't discuss further properties other than there are some algorithms to get these eigenvalues and eigenvectors, and in many cases these are complex, but we restrict our attention. So for a real symmetric, and then it's clear, so if it's real and symmetric, then the eigenvalues are all real. So the lambda I all real. So, and if this is the case, we can do a decomposition as follows. So, namely, we can write A as a product of u times lambda and u transpose. So this here is an orthogonal matrix. And this orthogonal matrix is composed of all eigenvectors. So the eigenvectors are orthonormal. Because if we write u transpose u is the identity matrix, and also u transpose, and this lambda here, lambda is a diagonal matrix containing all the eigenvalues. So that's a lambda, not an A. So let's correct it. So that's a good thing here. So that's our lambda. So that's the eigenvalue decomposition. So, and that's really, really fundamental. So just put this into a special thing, because this is one of the things we will encounter again and again and again. So we can decompose this matrix into the product of three matrices and two of them are orthogonal, and this is a diagonal matrix. And so we can, once we have the eigenvalues, we can actually say a lot of things about the matrix A. For instance, so if all the lambdas are positive, then we call A positive definite. If one or more of the lambdas are equal to 0, then A is singular. So this is something we will see occasionally in multivariate statistics, and we try to avoid it because we often would like to invert the matrix, and matrices that have 0 eigenvalues are basically difficult to invert. So related to this is also the notion of rank. So if all the eigenvalues are non-zero, then it has full rank. All lambda I non-zero, then full rank. And A is full rank. So then we have an interesting connection. So you can see eigenvalues are quite useful. So we know that the trace of a matrix is defined as the sum over the diagonal elements. And it turns out that it's also the sum of the eigenvalues. So this is something that's quite useful. And there's something called the determinant of a matrix, which is actually relatively tricky to define, but it's very easy to define. I mean, it's tricky to define in terms of the actual entries of the matrix, but it's very easy to define in terms of eigenvalues because it's simply the product of all eigenvalues. So the trace is the sum of the eigenvalues, and the determinant is the product of the eigenvalues. And you'll see in a few minutes that there's actually an interesting connection between the trace and the determinant. And before we can do this, we need to see how we can actually compute functions of matrices. And we only look at special type of functions, or special type of matrices, namely the symmetric real ones, so the easy ones that we can handle with the eigenvalue decomposition, and that we lead to real eigenvalues and not complex eigenvalues. So we have a function f, and we would like to apply to A. Turns out all we need to do is we do the eigenvalue decomposition, and then we apply the function on the eigenvalues. And then we basically put the thing together again. So that's the definition. And so an easy example would be matrix inversion. So how is this computed? So this is actually computed by taking the eigenvalue decomposition, then multiplying the eigensystem with the inverse of the eigenvalues times the transpose of the eigenvectors. And the idea is this is easy to compute because it's a diagonal matrix. Because it's a diagonal matrix, we can just apply it individually to the individual eigenvalues. So this would be the first eigenvalue inverted and so on, and everything else stays the same. So that's a nice thing when you have diagonal matrices, then you just apply it to the individual components. So the same fashion you can compute the matrix square root. So the matrix square root is simply u times lambda then the square root of the eigenvalues and u transform. And of course we know that, let's say we have 10 eigenvalues, then the square root we can have either a positive or negative sign, so we have two possibilities for each eigenvalue here. So we have many different square roots, so it's not unique, but we define the principal square root. The principal matrix square root is take the positive sign of the lambda I. So, and if it's all positive, then, and we do this here, then we get the principal matrix square root. And this is usually the matrix square root that we're using. So another commonly used operational matrix is the matrix exponential. And this is also defined exactly the same thing. So we just take the exponential of the eigenvalues, and the same with the log. So the matrix logarithm is just u log of lambda times u transpose. And this allows us to connect the dots with trace and determinant. So we from this we can easily see that the trace of log A is the same as log det A. So remember, so log determinant of A is just a number, so this, and we know that the determinant is the product of the eigenvalues. So, and then we take the log, whereas the logarithm of A has eigenvalues of log of the individual ones, so this would be log lambda, so the eigenvalue of log A has eigenvalues log lambda I, and trace is just the sum, so this is the sum over all I, and this is the product over I. You can easily see that, of course, this is the same, because the logarithm converts the product into a sum. So that's a nice identity that occasionally is also quite useful. So that's about it about matrix decomposition, except for one I forgot. So there's also something called the SVD, which is the singular value decomposition. And this is basically a generalization of the eigenvalue decomposition. So we have A. So in A, we're assuming that it's a square matrix, but now we can just use basically any matrix, and then we can write A as follows: dV transpose. So these are called singular values. So this is singular, a diagonal matrix of singular values. And then we have U and V are both orthogonal. And they also don't need to be complete orthogonal matrices. So one of them is usually square and the other one is not square. And the reason is because this doesn't need to be square as well. So, and this is a generalization of the eigenvalue. So we will make use of this occasionally, but not nearly as often as the eigenvalue decomposition. So as a last thing, so all of this stuff you should be familiar with. So we don't really use this in a very technical way or theoretical way. We'll just later use this mostly to decompose anything that has to do with the covariance matrix, because the covariance matrix is one of the most important matrices in multivariate statistics, and we can understand its behavior better by looking at the eigenvalues in the eigensystem. So that's one thing. So the next thing, the last thing that we need to discuss is a little bit of matrix calculus. And basically this has to do with things like gradient, Hessian matrix, and so on. So operations that act on functions and produce vectors and matrices. So let's assume we have a function. So we have f, and that's a function of a vector. So is a scalar valued function with vector argument. So then we can write down the gradient of this thing, and that turns out to be a vector, but a row vector in the convention we're using. And that's the first component is the first derivative of this function with regard to the first component, x1, and so on. And the last entry in this vector, row vector, is the partial derivative with regard to the last element in x. So that's the gradient. And it's in our notation, it's a row vector. And this is the nabla operator. I think you know this from last term, from the statistical methods class, where we used this to describe likelihood functions and like a first derivative to get estimates. So sometimes you have a vector valued function. So sometimes, when you have f is also a vector, then you can also compute the gradient for this. So but then it's not called, so this is basically a vector containing of functions, and the matrix containing all the gradients of these functions is called the Jacobian matrix. So Jacobian matrix is J, F, so that's the notation here, and that's simply a matrix where each row contains one gradient. So, and we will encounter this, of course, Jacobian matrix. And you can write it in various notations, but I'll usually stick to this Jacobian notation. Some people just like to write it like this. That's of course like extremely simplified, but it has the advantage that you can also write a gradient like this, so you don't have much different notation. But of course, so you need to always pay attention whether your function is vector valued or not. So that's the first derivative. And then we have also second derivatives. And the most important thing here would be the Hessian matrix. And that's simply you have a scalar valued function and you apply the gradient twice, basically. So it's the matrix of all second order derivatives. So one squared and so on. So this matrix contains all second order derivatives. So finally, last thing, you can also, so we've seen that we just took a derivative with regard to a vector, but you can also do this with regard to a matrix. And then you can basically, you have functions. So you can have something like this, f x, and you can actually define derivatives with regard to this x. And this becomes actually quite messy, but there are some special examples, so I'm not gonna detail any general rules for this. But you can, for instance, take the matrix derivative of the trace of something like this, so the trace of product A times X, so these are both matrices, and this is simply A, for instance. So this is one example, and another example would be the derivative of log det of X. So this is again a matrix. So these are all matrices. That's the important thing. So, and this turns out is just the inverse of X. So this is just the rules for matrix derivatives. Okay, so that's some of the things you need. The most important thing is actually the eigenvalue decomposition, so please have a closer look at the eigenvalue decomposition, and then next is the singular value decomposition and a few other things, and that's it for today. So I'll see you in the next class, where we will be talking about some elementary facts about multivariate random variables. Okay, bye bye.